All right, so welcome to our new Chem 115 lab adventure. I'm going to give you a little pre-lab for lab 10, the vitamin dilemma, a little bit of the background information that you're going to use in some of your explanations. And it builds off of lab 8, where we looked at the polarity and shape of molecules, whether the molecules could fit in between those DNA base pairs. So if you recall, we had some molecular formulas and we used those to draw Lewis structures, and we need to do this so that we can figure out the three-dimensional shape of molecules. Right? So we can't determine it based on the Lewis structure alone. We need to look at our central atom. In this case, it's easy because there's only one central atom, and use VSEPR. Remember, valence shell electron pair repulsion. So those electrons are all going to repel each other to get as far apart as possible in three-dimensional space. We have 4 areas of electrons here, so we have the 2 lone pairs, those are 2 areas, and then we have the 2 bonds, those are 2 areas, so 4 altogether. And when you have 4 areas of electrons that repel each other to get as far apart as possible in three-dimensional space, you get this tetrahedron, right? And so we say that the electron pair geometry or the root geometry is tetrahedral, right? But when we're thinking about the actual shape, we only think about the bonded atoms, right? So if we think about the shape of water, it's bent because these lone pairs up here are still taking up space. And in fact, the lone pairs repel a little bit more than the bonded electrons. And so if this was a perfect tetrahedron, all these bond angles would be equal and they'd be 109.5, but in water, they're closer to 104.5. Right? So once we have this shape, we then also have to think about the polarity of the molecule, right? And to do that, we need to think about not just the shape, but the bond polarity. So we know our bonds here are oxygen and hydrogen. Oxygen has a slightly negative charge because it's more electronegative. So when bonded to hydrogen, it pulls the electrons closer. Hydrogen has that slightly positive charge. And so when we take that in the context of the molecule, right, the oxygen is going to pull electrons towards it. So overall, it's going to have a slightly negative charge. The hydrogen end is going to have a slightly positive charge. So we say this molecule is polar or has a dipole. So it has a negative end and a positive end. So this asymmetrical distribution of charge, right? And whether a molecule is polar or not and how polar it is. So if you think of a polar molecule like a magnet, right, we know that there are different strength magnets. So stronger magnets will have stronger attractive forces between 2 magnets. Same kind of thing if you have molecules that are more polar, the attractive forces between one of these and another one of these is going to be stronger than for more weakly polar molecules, right? And these attractive forces between molecules are what we call intermolecular forces. And the types and strengths of these intermolecular forces for covalent compounds, which is what we're talking about here, impacts their properties like melting point, boiling point, viscosity. So some of the things we're going to be talking about today. So today we're really going to be focusing on those intermolecular forces. And it's really important to understand the difference between intermolecular forces and intramolecular forces. So for intermolecular forces, which we're really talking about when we talk about molecular or covalent compounds. So remember, covalent compounds are the ones where we have just nonmetals bonded together to form molecules. And the intermolecular forces are the attractive forces between molecules. So between 2 water molecules or between a water molecule and another molecule, right, we call those intermolecular forces. And they are affected by the polarity and the shape of molecules. So contrast those with intramolecular forces. Intramolecular forces are the attractive forces within a molecule. So think about intramurals, right? Where you play teams within your own school versus inter-school sports where you play between schools, right? So intramolecular forces are attractive forces within a molecule. Those are the covalent bonds in this case. They hold the atoms together, right? Whereas your intermolecular forces are the attractive forces between one molecule and another. So in order to have an intermolecular attraction, you have to have at least 2 molecules, right? The intramolecular forces, or the covalent bonds, they stabilize the individual molecules. So the strength of those bonds affects how stable a particular molecule is, whereas the intermolecular forces stabilize the bulk sample of matter, right? So they are what make water a liquid at room temperature. Intramolecular forces are much stronger, so these covalent bonds are much stronger within the molecules than the attractive forces between molecules. Right? When we're breaking an intramolecular force, we're breaking an actual bond. It takes a lot of energy. Right? When we're breaking intermolecular forces, we're pulling molecules away from each other. Right? So that's what we're doing when we're boiling something, excuse me, a covalent compound, or melting it. Right? So if we boil water, we are causing water molecules to get further from each other, but we're not actually breaking those hydrogen-oxygen bonds within the molecule. Right? So in this diagram here, the intermolecular forces are these dotted lines, so the attractive forces between molecules, and the intramolecular forces are the bonds between the atoms. So this is a representation of HCl, right? And remember, we think about these bonds as formed by that overlap between atomic or hybrid orbitals. Okay, so there are various types of intermolecular forces. You have some listed in your lab manual. There's a table in your lab manual that shows you a number of intermolecular forces. I have some different ones here, but all of the ones that are in your table in your lab manual are also in my table here. The table in your lab manual is on page 10.3 and 10.4. And that table also includes ionic bonding and covalent bonding at the bottom. The primary types of intermolecular forces that we talk about are these London dispersion forces, or you may have heard them called van der Waals forces. These are the only type of attractive forces that exist between nonpolar molecules. So these van der Waals forces exist between nonpolar molecules like fluorine and fluorine, right? They are caused by what we call instantaneous and induced dipoles. So at any time, if we think about the electrons being uniformly distributed in a molecule, at any given time it's possible to have more electrons at one side of a molecule than the other because they move around, right? And if that happens, then we have what's called the instantaneous dipole. So it happens one instant where we have more electrons on one side than the other. That means we have a slightly negative charge on one side. If that then gets close to another molecule, it can induce a dipole here. So it can repel electrons and cause this molecule to also have this asymmetric distribution of electrons temporarily, right, and form what we call this intermolecular London dispersion or van der Waals force between here. Right? Another type of intermolecular force that we talk about quite commonly is dipole-dipole. So these are the types of attractive forces between polar molecules, right? So ICl is polar, chlorine's more electronegative, pulls electrons towards it. So this molecule has a permanent dipole. The chlorine end is always slightly negative and the iodine end is always slightly positive. And so when two of these molecules interact, the negative end of one molecule will interact with the positive end of another molecule. And you can see by the kilojoules per mole, that's kind of a measure of the strength. These tend to be stronger than our London dispersion forces, although we can get strong London dispersion forces, especially for really big molecules, which is one of the things you will take a look at in the pre-lab for this lab, I believe. And again, we talked about the fact that these polar molecules, right, they can have a range, right, so they can be just a little bit polar, or they can be a lot polar. The more polar they are, the stronger the dipoles, the stronger the attractive forces between them. And then there's this case, this hydrogen bonding interaction, which is really just a special dipole-dipole interaction. So it happens in polar molecules, right? But only polar molecules that have a hydrogen that's bonded to a very electronegative atom. That electronegative atom represented A here has to be nitrogen, oxygen, or fluorine, right? And that hydrogen then interacts with an oxygen, nitrogen, or fluorine in another molecule, right? So here's an example that hydrogen, it's bonded to one of those, it's bonded to an oxygen, so really polar bond, and that hydrogen interacts with an oxygen in another molecule. That's what we call a hydrogen bonding interaction. It is an intermolecular force. It is just like a dipole-dipole, but it's a really strong dipole-dipole, right? So you can see it's in general stronger than the dipole-dipoles, and so we give it a special name. The other kind of interaction that you may want to be familiar with are these ion dipoles, and these are the types of interactions that form when things like sodium chloride, table salt, dissolve in water. So when sodium chloride dissolves in water, the sodium chloride lattice, right, those ions, they break up into individual ions, and the sodium ions, the positive ones, are surrounded by water, surrounded by the negative end of water, right? So we'd have water molecules all around the sodium ion, and then the chloride ions, of course, are surrounded by water as well, but the positive end. So the chloride ion would be surrounded by the hydrogen end of waters, and that's what helps these compounds dissolve in water. All right, so to make sure, to kind of test your understanding here, I have three different interactions. I want you to tell me what kind they are, right? Are they intra or inter? And if they're inter, what kind of intermolecular attraction they are? And then which attractive force is strongest? And you should be able to justify your answer. Right, so take a minute and do that. If you need a little bit more time, you should pause the video because you should make sure you can do this before you move on. But we're going to talk about these, right? So these dotted lines here, they represent intermolecular attractive forces between two molecules, whereas this is an intra, right? You cannot have intermolecular attractions if you only have one molecule. It has to be between molecules, right? So this is an intra, this is a covalent bond. These two are intermolecular attractions, right? This is between two polar molecules, so I have a slightly negative oxygen here and slightly positive carbon there. The slightly negative oxygen interacting with the slightly positive carbon. So this would be a dipole-dipole interaction, right? I could have also had the slightly negative oxygen interacting with the slightly positive hydrogen. That would still be a dipole-dipole interaction. It would not be a hydrogen bonding interaction, right? Because the hydrogen is not bonded to an oxygen or nitrogen or fluorine. Right, so this is not a really polar bond. This, on the other hand, is what we call a hydrogen bonding interaction because our hydrogen is bonded to an oxygen and then is interacting with an oxygen in another molecule. So which one is the strongest? Well, we talked about the fact that the intramolecular forces are much stronger. Those covalent bonds are much stronger than the attractive forces between molecules, right? And that's something that's important to remember. If we think about that, if we actually look at the energy, if you think about breaking that oxygen-hydrogen bond in water, it takes 400 kilojoules of energy to break 1 mole of those OH bonds, but only 16 kilojoules of energy to break a mole of those of the hydrogen bonding interactions, the intermolecular attractions. And then if we think about the dipole-dipole attraction, in this case in acetone, it takes only 4 to 8 kilojoules of energy, so weaker than the hydrogen bonding interaction, but both of them much weaker than that covalent bonding interaction. Okay, so that takes us to our lab and our goals and skills. So we want to investigate the effects of molecule polarity on its interactions with various liquids and use the results of your investigation to determine whether it's safer for your friend to take megadoses of vitamin C or vitamin E. So we're going to be able to do that by the end of this lab. We're going to be making some observations about interactions of substances using evaporation rates and viscosity and solubilities, whether things mix with each other or not. We're also going to be using mole view again. So remember we did that in the last lab. We're going to be using mole view to examine 3D molecular structures as well. So in part A, you're going to examine the evaporation rates of 3 substances. You'll watch videos and look at the evaporation rates. You're going to need to explain your observations using the concepts of intermolecular forces that I just talked about. So what is the strength of the what is the relationship between the strength of the intermolecular force and its boiling point or its evaporation rate, right? If it evaporates fast, what does that mean? Are there strong attractive forces between molecules or weak attractive forces between molecules? And how do you know, right? In part B, you're going to examine the viscosity of different liquids. So the viscosity is a measure of the resistance to flow. So think of honey. Honey flows really slowly, so we say it's very viscous, right? Think about what is the relationship between the attractive force between molecules and viscosity. Do you think that if something has strong attractive forces between molecules, is it going to have really slow flow or is it going to have a faster flow? In part C, we're going to examine the solubility of different substances in water and oil. Um, and so whether something mixes with water, a polar substance, or oil, a nonpolar substance, is going to tell you something about the types of attractive forces between the the molecules. You're also going to need to use MolView for this part as well. And then the last part, we're going to explore the structures of vitamins using MolView. All right, so that's it for this pre-lab. You have some videos to watch. You have a form to fill out. So good luck.